Hey folks, good afternoon. Hope everyone's doing well. The the webinar is going to start in shortly. We're just going to wait for 2 to 3 minutes for people to join in, connect to their audio, and probably get a cup of coffee. So thank you for your patience, and we'll get started soon. Folks, we're just going to give it another more minute before we get started. Just waiting for the attendees to join in and connect to their audio, and we shall have the session begin just a minute or two. Thank you very much. All right, folks. Thank you very much for joining today's webinar. So, my name is Yafis Siddiqui, and I'll be the host for today. And so, for those joining in, I guess we'll just start with understanding today's session. So, the topic is going to be on lightweighting electric vehicle platforms and systems. Uh, Today's session is going to be led by Martin Gambling from from GRM Consulting. Just For those who are unaware, this is part two of a series surrounding electric vehicle. We had a part one that was around battery design. Today's session is most around structural analysis as well as optimization around structural analysis. So just a quick introduction. So like I mentioned, my name is Yafa Siddiqui. I am the pre-sales manager at Maya Heat Transfer Technologies, and today's presenter is Martin Gambling. Martin, do you want to introduce yourself?
Yes, certainly. Hi, and welcome to all of you. I'll even be brave and see if it works. Pop my camera on. So, hello, everybody. I'm not sure if I'm appearing on screen anywhere, whether we do when we
Yeah,
present.
we can see
But
you, Martin.
you can see me. Great.
Yeah.
Okay, wonderful. Yep, I'm looking forward to presenting today.
Perfect, perfect. Okay, wonderful. Right. So before we get started, I just thought maybe I'd spend a few minutes just introducing who Maya are and what we do. So Maya HCT or Maya Heat Transfer Technologies, we're a software-driven engineering solutions company. We were awarded the worldwide partner for Siemens. Essentially, we enable companies to create a digital twin of their engineering processes. We started in space 30 years ago, but we've expanded to various industries: electronics, electric vehicles, aerospace, defense, so on and so forth. We are a technically focused company with 75% of the staff scientists and engineers. Not only do we provide solutions or services, but we also produce 30 plus software modules for Siemens as well. So in terms of the services and solutions we provide, I'd consider us as a one-stop solution or one-stop shop related to engineering or virtual or digital twin, or creating a digital twin of your engineering process. So we can provide services from design, simulation, manufacturing in terms of computer-aided manufacturing or CAM. We do provide industrial IoT and applied AI services. One of our big specialization is in software development and custom application, as mentioned earlier. We do provide automation and optimization capabilities, as well as deployment of PLM systems such as Teamcenter. So let me just pass it on to the next slide to just a second. Oh, there you go. All right,
It's me.
Arnen, you want to take over?
Absolutely. Thanks, Jeffers.
Thank you very much.
Okay. Thanks for the introduction, and good afternoon to everybody. Good evening if you're in the UK like myself. You may have had a keen eye and spotted it's very much nighttime where I am. It's the evening here in the UK. So I'm going to be talking for hopefully around about 35 minutes, maybe 40 minutes, about lightweighting of EVs, and I'm going to break that down into a few different topics. First of all, I'm going to start talking about optimization driven design, what that means and how it compares to, I guess, non-optimization driven design. Then I'll have a brief discussion of the tools we're talking about today. So that's SimCenter 3D, simulation, and the optimization tools that we embed within it. Before we'll get on to, I guess, what's ultimately the interesting bit, which is the applications to EV, where I'll show you some of the tools in action with some applications to battery boxes, suspension components, and so on the EV platforms. And then we'll wrap up with a summary and have an opportunity for some questions at the end. Okay, so first of all, the big question: what is optimization driven design? So I guess a lot of us on the call on the webinar may have come across optimization and seen it used at certain points in a process. But really what we mean when we talk about a driven design philosophy is actually embedding optimization into your development workflow. So that's having the tools at the right moment for early concept, developing architectures, and even down into detailed developments, using optimization at each of these stages, such that we can really leverage it in the right way to both get us better designs, but also to save us time. A lot of us often realize that we can get stuck in a whole world of iterating through simulation, and all of a sudden time has passed by on our deadlines. So seeing how we can help you there, and also using it to resolve design issues along the way. Okay. So in terms of how it works, what we're talking about when we're referring to this FEA-based optimization philosophy, if we first start off by taking a look at what we do already. Now, this in itself is an amazingly powerful workflow using simulation tools to predict performance and to engineer in the virtual world. This is something you'll see in SimCenter as a very broad spectrum of capabilities. You've seen some in our last webinar as well. But here with FEA, this is the workflow that we typically follow. So we'll do an FEA simulation. We'll take a look at that performance. So what are our stresses? What are our displacements or natural frequencies? How is the part performing? And then we go through and we say to ourselves, oh, is this good enough? Is this meeting our performance target? If it is, we stop. If it's not, then we're going to use our experience and maybe some calculations to make a decision on how we're going to revise a design before going back to design, updating our master design or making some manipulation of our models and redoing the simulation. So this is pretty much how it's done through simulation, iterating your designs. And if we take a look at optimization, and the flowchart now I'm showing is one that's describing what's happening in an optimization solver, in the ones that we're going to be talking about today. So really, a similar things going on, just with some different names and some different tasks. So we do our FEA analysis, and then we're reviewing now what we're going to be calling our goal or objective, and also checking our constraints. So that's essentially the optimization, reviewing performance. Then we look at convergence. So that's the optimization evaluating, is the performance meeting the criteria? Do I think I've got it as good as I can? And if I do, I stop. And if I don't, then we're then able to internally calculate sensitivities, which is how a design response changes to a design change. And with that information internally within the optimizer will then perform an optimization to say, how should I change the design within certain limits before automatically updating my design and looping through to analysis. So essentially, if you put the two processes side by side, they're really very similar. Some of the key benefits with the one on the right are it's automated. So we're automatically evaluating responses. We can automatically update our design and remove the need for a human to have to iterate in the process. And the key thing here is obviously communicating the right information into the optimization tools so that it is iterating in the right way and going in the right direction. And that's part of what I'll aim to discuss and show you today. And one of the key strengths you'll see with the optimization solvers is their ability to consider multiple load cases. This is a really important one and a big one, particularly on EV systems, where there's a lot of competing requirements that we need to satisfy in our design. So why should we use these tools? What's the benefit for us, really? Why do we want to take it on? So first of all, when we use them correctly, we can develop designs faster. In theory, better designs at the same time. And what we're often doing is looking to maximize the potential of our designs, particularly focusing on the manufacturing method, the design approach that we've assumed for the design. So good examples would be a casting, where we can tune and tailor the thickness of a part. With castings, we do have that flexibility. So taking advantage of that and connecting that flexibility in manufacture with a tool that can really make the most of it is why we should use optimization. And if you are working in the field of composites, we won't discuss it much today. There's a lot more to be discussed in that arena. But if you are, optimization and composite materials really do complement very well because of that inherent flexibility in the material and how you can tune and tailor the performance of your structure. And you have an optimization tool that can manage that within it. A big one that's often not talked about or forgotten about with optimization is saving time and freeing up engineering time. If the task is to iterate the thickness of a part, doing that through simulation after simulation after simulation takes time, and setting the goals to an optimizer and asking it to do it for you is just simply freeing up that engineering resource, and that's a really significant one, as well as getting that best design across those multiple load cases as well. And so I've sort of jumped ahead on the points there. You can see that being able to tailor your design to meet those multiple requirements is really quite key. And so as you'll see in some of the examples, we can optimize for stiffness and for stress and vibration all at the same time within the optimization, looking to develop that best compromise against these requirements. And so we often talk in optimization about minimizing mass. This is really key when you start looking at mass budgets for electric vehicles. And if you go a little bit over on each of the different systems, you find all of a sudden the total vehicle weight is escalating. So keeping that in control is key. But it also lends itself to material usage reductions, which inherently then lead to cost reductions. So even just something as small as a 5% reduction in material can have a really significant reduction in material costs in manufacturing. And then what often happens when you do have lots of different disciplines, we've seen this in other sectors, is developing different concept designs and then evaluating those to the best of their particular abilities through optimization allows you to really rapidly compare the feasibility of multiple concepts and see which ones win out when you engineer them down a certain path. So in terms of using these tools, my personal background is I've used them a lot in competition applications, so areas such as Formula One and motorsport, in marine in the America's Cup, and that in that arena they're really focused on performance. That's the driving metric. Can I get a little bit more performance to go and win? But the tools themselves, as you hopefully seen from above, really are so much more than that. They're just making the engineering process more simple, solving problems, reducing material usage, and saving you time along the way. So we're on to poll question number 1. So Yafis, back to your good self, if you could.
Perfect, wonderful. Thank you very much, Martin. So folks, on your screen, you should be able to see the poll. So the poll question is, do you use SimCenter 3D, previously known as NX or CAE, and SimCenter Nastran for your structural analysis? So there are 3 options available. Yes, we use SimCenter 3D and Nastran for all our FEA. Option number 2 is yes, we use SimCenter 3D and Nastran for some of our FEA. And the last option is no, we do not currently use SimCenter 3D or Nastran. So you should be able to see the poll on the right-hand side of the GoToWebinar. Folks, just a reminder, if you have any questions, please don't hesitate to drop it in the chat. We'll definitely address it today, or we'll get back to you via email after the session. So I can see the polls coming in. We're just going to give another 30 seconds for everyone to put in their answers. So the poll question again is, do you use SimCenter 3D and SimCenter Nastran for your structural analysis? So the first option is yes for all, second is yes for some, and third option is no, we do not currently use SimCenter 3D or Nastran. Perfect. We're just going to give another 20 more seconds for people to put in their answers. And I guess we can close the poll. Perfect. So I am just checking in. How do I share the results? This is it. So regarding this poll, so majority of the users, 61% of those who voted, do not use SimCenter 3D or Nastran, with the 22% use all, with the rest with some of them. So hopefully by the end of the presentation, we're going to make sure that we all convince you to all use SimCenter 3D and Nastran for all your FEA. Martin, go ahead.
Brilliant. Thanks very much, Yafis. Excellent. Okay, so that's great to get that feedback. Before I go into these next few slides, it helps me to understand the audience and what I need to be updating in terms of the tools. So I'm going to give just a short introduction, just a few slides now on SimCenter 3D, SimCenter Nastran, and OptiAssist, which is the product that we're talking about in question here for the optimization technology. So the big question is, what is SimCenter 3D? Even if you're not using it, maybe you already know what it is. When I got involved in working with Siemens and SimCenter 3D, and I went to their the first conference I went to, the SimCenter conference, I was amazed at how many disciplines it covered and how comprehensive it was. So I think you see on the image on the left there, the different arenas where simulation can be performed within SimCenter 3D. And the key basis of it is this common engineering desktop to perform these simulations. That's a really key strength. So you can be running from a single design out to the different disciplines and different solutions. And each of these, there's really some significant and powerful and reliable solvers for each of these different disciplines. Today we're focusing, where are we on around the clock? In structures. That's the primary area for today. But as you can see, particularly for EVs, this is really a powerful set of tools. Okay, and I think from my experience of it, the biggest strength of SimCenter is its integration of all these tools together, having the ability to manage your design within NX, if that's your chosen design platform, and then connecting through to SimCenter is really key. But even if you're not in NX and you're just working in the SimCenter environment, having that common platform is really a key strength for managing your data and connecting all these simulations together. So in terms of what this means for EV developments, that's quite an important question for today. I think the key thing with engineering electric vehicles is there's a lot of technology and methods that's common to IC engine vehicles, but there's also a lot of technology that is new, and simulation techniques are developing for those all the time. And if you were able to join us for our last webinar in this series, you'll have seen some of the methods available for battery modeling in terms of the various calculations for thermal management, energy calculations, and so on. Okay, but further to that, as we'll go through today, it's got a real depth of tools for structures, but also in terms of the motion, the driveline simulation, dynamics, acoustics, and EM calculations for EVs. So really quite a extensive range of tools for all of your simulation needs. So I guess, how does that help you? That's the key thing, really. I think the key thing is the tools allow you to model either using efficient lean simulation tools to get fast simulations, or to delve into the detail if you want to and model in great detail some of the complex systems in your designs. So that's all available to you in the simulation tools available in SimCenter 3D. And I guess these last 2 points are quite significant for what I'm going to talk about in terms of the details next, which is how the tools are all integrated together, which is where OptiAssist is fitted into SimCenter, and we can explore our designs, and that's through the optimization tools that we're going to be showing you in just a moment. So that leads me on to OptiAssist. As introduced, so I work at GRM Consulting, which is a company in the UK, and we are a technology partner to Siemens Digital Industries. And so we develop OptiAssist for SimCenter 3D, which is an extension to the SimCenter 3 environment, and it's bringing the structural optimization tools available to you within SimCenter. And really what we're looking at on the screen now are how the tools enable you to change your design. So in each of these cases, you're going to be setting a goal for the optimization that you're trying to do, minimize mass, maximize stiffness or frequency, and then you can set constraints and targets to meet. But in each case, you want to tell the optimizer how you can change your design, and that's what we're looking at for these methods. So they'll become more apparent in the demonstrations I'll be going through shortly, but you can see just in a very simple highlight, we have the ability to add form to thin structures, to optimize for thickness on each panel, to optimize through varying regions of your structure for castings and moldings, to tune the geometry of a design through FreeShape, and then to optimize your laminate definitions in composites. So on to the question itself, lightweighting EVs. Where can we use this technology, and what do we want to lightweight? So if we take a look at our systems, one we will look at today is lightweighting your battery housings. So we're not going to look at the batteries technology itself. We want more the housing, which has to be really quite a strong structure. There's a lot of different international requirements for the battery housing and its structural integrity. So you've got to make it strong, but manage the weight at the same time. Next, the EDU, so the transmission housings. These are often very large, heavy castings, and there's a lot of torque going through these electric drive units. So managing and maintaining the stiffness is really key, and the strength of these housings. So again, maximizing the efficiency of your materials is going to be a key area to take advantage of. Suspension components, we'll also look at that today. EVs are not always the lightest vehicles. I think we all know the challenges that we're facing here with the technology we have to carry on board. So making sure that we maximize the efficiency of all the suspension components so that they're strong enough, stiff enough, and yet they're coping with the loads in a weight efficient way. And then a pretty major one, a lot of OEMs will focus on this because of its inherent nature of the fundamental backbone of your vehicle, and that's the body architecture. So the body in white of the EVs. This is a different architecture logic to conventional ICE engines because of the platforms and the systems we're embedding, and you see that with the developing vehicles out in the market today. And then lastly, something that's often not really focused on, but there's a lot of mass to be saved, which is the interior structures. So here we've got seats, center consoles, instrument panels, a lot of metalwork underneath to manage, and even the trim parts themselves can be managed. So there's real opportunities for weight saving in this area as well. So we come around to poll question number 2 quite quickly, and the last one is at the very end. So back to yourself, Jeffers.
Thanks, Martin. Wonderful. All right. So poll number 2, hopefully you guys see that on the screen. I'm going to read it out loud. So what is the greatest challenge you face in engineering your electric vehicle structures? So there are 4 options. One is managing the total mass while meeting the structural targets. Option number 2, keeping to project timescales as the design is developed. Option number 3 is rapidly resolving performance issues. And the option number 4 is other. And for folks who put in other, you're more than welcome to drop it in the chat so that we can you can share what are those challenges that you face there. So I'm just going to read the questions out again. So it's what is the greatest challenge you face when engineering your EV structure? Number 1 is managing the total mass while meeting the structural targets. 2 is keeping the project timescales as the design is developed. 3 is rapidly resolving the performance issues, could be a multi-physics problem. And 4th one is other. So I'm just going to give it another 30 seconds for folks to take the time to vote. And yeah, if you do have any questions throughout the presentation, please don't hesitate to drop it in the chat, and we'll definitely address it by the end of the session, hopefully. Otherwise, we'll reach out to you after the meeting. So I'm going to give another 20 seconds for folks to put in their votes. So Martin, just curious to know, from your experience, from your customers, I know you're going to talk about this in a moment. What part of that EV structure do you most likely, people focus on more than the other? Is it the?
Well, I think actually historically it has been the body, and that's one of the things we see. A lot of people focus on body architecture with optimization methods, but myself then working sort of with other companies over the years, I've seen that there's a lot more benefit to be had in other disciplines, in suspension components, in interior systems as well. But yeah, I think it's putting that attention to detail in every area and adopting this philosophy is the way to get the best out of it. Because if you put all your effort into one area, you often miss great opportunities elsewhere. So I think that's the key thing we want to be achieving here.
Perfect. Yeah, that makes sense. So essentially, we use optimization everywhere we can possibly.
It's the key thing, and if we embrace it in the right way, that it's part of your development strategy rather than something you tag on at the end or you do a little bit at the start, then it becomes something that it just gets you the better solutions, and it also just gets you out of trouble quite quick, easily. That's a real strength. So resolving those issues for me is one of the key strengths of it.
Oh, perfect, perfect. All right, folks. So I'm gonna close the poll in a moment and share the results. Thank you for that, Martin. We'll definitely have a greater discussion on that, I guess, today for the next upcoming slide. So let me share the results now, and we seem to be equally having challenges everywhere.
That's quite a mix.
That's exactly it. I actually have a comment out here stating all of the above plus meeting the cost targets. So
Yes.
that's one of the parameters that could be input into your optimization algorithm specifically. All right, wonderful. All right, so Martin, I guess you have a lot of challenges to resolve in the next upcoming slides. Do you want to
Okay, brilliant. Thank
take
you.
over?
It's just click a button. It's magic. We all know engineering is rarely a magical button, but if we can have tools that can help us along the way, that's what we want. Okay,
Perfect.
so now getting into, I think, probably the most interesting part of the webinar, I hope, which is looking at some of the examples, and we'll have some demonstrations of the tools in action, looking at these case studies that you can see on screen now. So we'll start off with Team Sonnenwagen Aachen. Now, these are a great bunch that I was fortunate to become involved with through working with Siemens in Germany. So this is actually a student competing team in Aachen University, but I've been so impressed by how professional they've been in their engineering, their approach, and put some engineering companies to shame by their professionalism. So a really good example to be talking about in terms of what they do. And in terms of what they are doing, so they are engineering and competing in the World Solar Challenge, which is a series of events where they have to engineer and manufacture a solar-powered car to compete along vast distances. So they've just come back very recently, I think in the last month, from the Solar Challenge Morocco, which, as you'll probably have guessed, was in Morocco. And that was a race competing over 2,500 kilometers at the base of the Atlas Mountains. And there they just had to travel as fast as possible and actually get the vehicle all its own power from the sun across the distance as fast as possible. So they are using SimCenter not just for this optimization, but for the whole simulation environment, and also designing in the Siemens NX world. So this is a great demonstration of all the tools integrated together. Now, they've used the techniques for several applications, but what we're going to focus on now is just one demonstration of how they've used it in one of their earlier developing parts on a suspension swing arm. So this I'll load up in a moment now. And what you can see here is the rear swing arm for their single rear wheel in their solar vehicle. And this has been simulated in NX and SimCenter 3D. And here we're just going to take a look at two of the load cases that they're studying. So we've got a vertical load and then an axial load that actually is causing this lateral bending of the part that you can see on screen now. So in this particular instance, they have developed the part such that it is now meeting performance, and they want to investigate how they can maintain the stiffness of the part but take some weight out. This is what they're going to do. So they're going to utilize Optisys free shape optimization technology and allow it to make changes to the surfaces of the part to add material, remove material in small amounts, and see where it wants to refine the design. So first of all, you can see on screen now the inner holes, they're allowed to move in and out by a prescribed distance in their normal direction. And then on the outside, only a selected region, selected regions can be moved. As you can see, again, plus and minus 3 millimeters. So in terms of what they want to do, so as you can see in the interface, now we're walking through the setup process, and this is how the optimization is set up. And in this particular example, they're looking to maximize the stiffness of the part. So you just choose that as the goal for the optimization. And then what they've done is they said, well, actually, I'm going to define a mass for the part that's 15% lower than my current mass. So go and be as good as you can. That's the target they want. Now, in this particular example, they haven't defined any specific constraints for stiffness or stress. They just want to make it as efficient as possible whilst achieving that 15% saving. So at this moment, they've run the optimization within SimCenter Nastran, and once they've got the results, they're plotting their objective function, which is their goal, and they are also going to look at the constraint, which in this case is their target mass. And what you can see in this graph at the moment is, whilst having an initial increase in this what's called a compliance response, that then is brought back down again to almost its original position. So we've seen largely no change in the stiffness of the part, but the constraint, which was our mass, has been reduced from a violation of 15% down to 0, giving us that improvement in weight reduction. And what you can see now on screen is where it's looking to change the surface position. So you can see anything shown in red is where it's moved material either in or out. In some cases in to reduce the mass, and other areas around this hinge point is where it's actually brought material out to improve the stiffness. And then once they've got that, if they want to surpass that as a surface back to design so they can engineer around it, they can update their FEM and SIM directly from the geometry, and you can see how the mesh has been moved away from the surfaces to identify that best updated geometry. So it's as easy as that, really. And actually, all joking aside, it is as easy as that. It's not something that is separate to your day-to-day analysis. You're doing the simulation anyway. You've got this model in SimCenter and you've analyzed it in SimCenter Nastran. To add the optimization in there, it really is straightforward. So they've applied this to several of their mechanical systems, metallic mechanical systems, but also in their composite laminate development as well. And through taking this approach across the design, they've been able to engineer their latest solar vehicle, Challenger, which is the Photon vehicle, to a total mass of just 180 kilos. That's really, really impressive. And there we go. They even made one like that. So if you can take the time to stare at that, you'll find that various surfaces and these different wall thicknesses have been tuned based upon that free shape optimization. Okay, so now we'll move on to our second example, which is the battery housing. And this is titled mass reduction, but actually it's a little bit of problem solving and mass reduction at the same time, as you'll see in a moment. So what we're looking at here is this battery housing, which is a mixture of a cast main housing. Batteries are inside, various mounting arrangements, and then a cover plate inside. Now, in this particular application, they're looking to meet the EC 100 safety regulations for batteries and battery housings. So that in this study is focusing on 3 strength cases. So we've got a 10-ton crush load, which is a pretty heavy load, and then 15G acceleration loads in vertical and 28G acceleration in lateral. And further to that, none of the housing or assembly must exhibit any vibration modes below 50 Hertz. So that's something to resolve. And that leads us into the first part of this application. So this is 2 different studies have been performed on this assembly. First of all, it's looking to resolve a modal issue they had with the battery housing cover, where at the initial assumed thickness and design with some fairly simple swaging, not too much, it was down at 26 Hertz, so well below their target. So here they deployed topography optimization. This is the process of moving the form of a thin structure to see how they could resolve that issue. So here's the mode in question. Pretty clear first mode of the battery housing cover, which is at 26 Hertz. And so what they're doing is using the topography optimization process inside SimCenter and OptiAssist. And again, you'll see this common workflow in each of these demonstrations. This is the common flow of setting up and managing the optimization inside SimCenter and OptiAssist. So here, just the single load case of that first mode. And then for topography, what the user does is assign rules to the different mesh collector panels. So here, what we're looking at is, I'll just pause that a moment, the ability to define how the optimizer can change the form of your part. So here we're saying I can move plus or minus 7 millimeters. So not too much, but you can get that significant gain in that. The direction and the mirror symmetry. And here we can set different rules for pattern repetitions or linear patterns in the construction of the form that's being created. So here we're keeping it relatively free, but we're just adding mirror symmetry about 2 planes, as you can see have been selected in this particular example. Okay, so once assigned, here our goal is maximize frequency. Nice and clear, we know what we want to achieve. And then the rest of the setup is straightforward. So again, this is solved. You can see the buttons of solve or export. You can run it on a cluster, or you can solve it locally depending on how your systems work. And this graph is now showing the optimization objective or goal, which has gone from our 25.6 up to a frequency above 50 Hertz as our target. And so we can evaluate how that looks. Take a look at the last cycle of the optimizations. There's 15 cycles of it's taken to solve that. And here you can see the form it's developed. And whilst you see there's sort of a level of noise and pattern over it, there's a very clear form that you can interpret around, and that's exactly what they've done in this solution. Again, you can update that form directly inside SimCenter, so you can generate a new sim and fem file with that geometry, which you can then overlay with your design and develop around it. Okay. Great. So just to summarize that particular study, you can see without having to add any material at all, it's the same part, just moving that form, we've resolved that frequency issue. And in terms of how it's interpreted, sometimes it looks a bit daunting, but you can see here these sketches are pretty much what it's telling you to do. So have a nice clear, rather than a classical straight form, having a curved depression in the section is more efficient, and then edge swaging in the form. So next, we are looking at the main casting itself. So this is a little bit further downstream in the development. So the design is now meeting the targets, but there's not really been the time or the effort spent to explore, can I make it lighter? And that's where do you start? You've got the first mode of the batteries bouncing inside the system. You've got these 3 different strength load cases. So to try and iterate them and assess each one individually is where you tend to just stop. And so here you can see how this process of managing the multiple load cases is able to be done. So here we're inside SimCenter with a Nastran solution, and we've actually got 2 studies. One is our static solution of our strength cases, and the other one is our modal analysis. And this is the part we're working on. So this is a fairly large casting that's housing the batteries, and now we're using the thickness optimization to work on the setup. So as opposed to the vibration problem, first of all, where we had 1 load case, you can see now we're going to be considering the 3 strength cases and the vibration case. Oops, I just go back just a moment so we can see that. So in a similar layout to the topography approach, thickness works in the same way, where we create rules on what we're going to change, and then we assign them to the mesh collectors that we wish to design. And so in the case here, we're going to be changing the thickness between a range, as you see there. And then we're also going to create a second rule, which is called subdivision. So you can do this in many different ways, either by geometry face, manual patches, feature angle, or in this case, just a simple grid in space. That gives it good freedom. And here you could start to choose whether it's a local or a local orientation of the splitting, whether they have mirror symmetry and so on. And these small patches that you're seeing on screen are the different regions where thickness can be varied. So you have the ability to control that yourself. So depending on how much complexity you want to add or not is how you can develop your design. In this instance, we're looking to minimize mass as our goal. So with that in mind, we then need to set some constraints that it must meet whilst minimizing that mass. So first of all, we're setting a target that the natural frequency must be greater than 50 Hertz. And that's here you can see you can choose which mode. So if it's not the first mode, you can set it to an alternate mode. In this case, it is. And then secondly, for the 3 different strength cases, we want to constrain our stress to 125 megapascals. Okay, as ever, that's then solved in Nastran, and we can look at our results. And in this instance, the objective is your mass. That's what we set as our goal. So you can see now how that's been reduced. And we'll look at a summary of that in a moment. And then we can go ahead and review that thickness. And really it becomes pretty clear that actually with the right placement of thickness in a few key areas, then there's a lot of flexibility to reduce material elsewhere and still achieve those strength and vibration targets. So really a good example of how that technology works. So just to summarize the whole study, so through that exercise, there's then a little bit of interpretation, which is working with optimization coupled with your engineering brain. They've ended up with a design that is 7.5 kilos lighter than they were at, and we've resolved the design issues, the performance issues along the way. So lastly, I'm going to talk to you about actually a developing technology within our SimCenter based OptiSys tool, which is something called RDM. So this is called the reinforcement derivation method. So this is really utilizing the technology of topology optimization. Some of you on the call may be very familiar with that technology, some may not. But topology allows you to evolve the layout of structures from a package volume. But what we're trying to do here is not just start from scratch, because it's very rare that we start from scratch with a design. We're often developing with commonality from different platforms or different systems. But as we're developing, we have issues, we want to resolve them. So being able to leverage topology in that workflow is key. So if I just take you through how it works, first of all, we've got our simulation of our part. Then we want to understand, if I'm not meeting my targets, what have I got to do? So then the RDM interface in OptiSys will automatically generate candidate material for you within a set of rules. What you see on screen is something called a block search. It's immersing your design in candidate material and connecting that candidate material to your structure. And then you run the Nastran topology optimization with set targets, and it will identify where you want material. Now, in this body architecture example, what we're seeing is not that we want to have blobs of material added, as you see here, but this is identifying where you want to put your engineering effort. So in some instances, it might be a new load path that's efficient to do. In some areas, it might be reworking geometry. Once you look at it and see what's happening, it may become apparent. And then sometimes with very small lumps of material you see here, it's just saying, I need to improve my connection strategy between parts. And that's a key process in itself. And you can see this process in action in other parts too, not just bodies, but in systems. So here we've got a clutch housing as an application. So if we take a philosophy right from the outset that we're going to use this technology, then we design a part, as you see on the left, as a minimum envelope. So this is a real functional design, but we're going into this design knowing that we're going to be probably failing structural performance. But we've got all the functional attributes there. So the bearing carriers, the fixing points, the oil retention. We're not trying to make it strong enough by adding and second guessing where ribs and extra thickness should be added. But we use RDM on top of our part in a series of iterative loops. So here you can see where material was added. And so the designer and the engineer work with this to develop new details based upon this optimization. So you can see the ribs forming as you see here. But it's still not meeting performance, much better, much closer. So then we combine our interpretation that we could do with another loop of RDM until we end up with these extra ribs and extra thickness to complete our design. Okay, and this particular example was done by Tata looking to replace an existing part, and it took the previous housing from 6.7 kilos down to 5.7 kilos. So that's a whole kilo off the part on just a single component in the system. Sometimes doesn't seem too much, but a kilo on a volume produced cast part is really significant in terms of the cost. And I see there was that question early on about meeting cost targets. A kilo less material in your cast part is a big cost saving. So somebody else who's using this more on the architecture level, this is an early screenshot of some of the work that we're doing. As mentioned, this is a development feature of OptiAssist that we are looking to release in the new year. And so Bristol Superlight have been using it to help develop their architecture, again, through extending the use of topology throughout the development cycle. Okay, thankfully I'm at the end in the sense that it's 10 to 6 here in the UK, I should say. So I'm good on time. So just to summarize, hopefully what you've seen, for those of you that are using SimCenter or not, is that SimCenter 3D, and with the addition of OptiAssist, provides really a well integrated and powerful simulation and optimization tool set for EV structures. With all the different functionality and solvers within, it's a really powerful platform for the different requirements we need to engineer for in the development of EVs. SimCenter's common engineering desktop does provide that common environment for the different simulation attributes we need to perform. If you're working in NX as well, it's entirely seamless with your design workflows as well. And so OptiAssist is that tool that enables you to apply this optimization driven design philosophy into your designs, and hopefully you can see it's not really a leap. There's very little to go from where you are in simulating to adding optimization. There's no cost to your effort. It's there, it saves you time, it gives you better answers. And so really that's I think the key takeaway I really want to say. You probably have gathered a real big fan of optimization when used correctly and embraced with the right engineering. So we're going to end with a last question, if I can. And back to yourself, Yefes.
Perfect. Thank you very much, Martin. That was quite great examples out there. So I'm going to launch the last poll. We do have a few questions in the chat that we'll take some time to. So this might be a quick poll. So folks, the question here is, what is your preferred method of learning more about lightweighting technology shown today? Would you want a one-on-one meeting, a technology benchmark, doing some training and software evaluation, or software lease or purchase? So I'll give you guys a few moments to answer your preferred method of learning more about the lightweighting technology shown today. In the meantime, I think I can take some time as well to read out the questions that we have here for you, Martin. So
Great,
one of the yeah, sure. Can you see the question that's right out there? I'll read it out.
I can see a couple there, but please read it out. It's helpful, isn't it? So.
Perfect, wonderful. So are composite materials safely used in the battery elements in the structural design? And if yes, what are the challenges and how are these solved, especially at the battery certification level? So were the composite materials used? If yes, and what are the challenges with using composite material and how are they solved at the battery certification level?
So my understanding is that in certain applications they are used. There are challenges. I think one of the biggest challenges in terms of using composite materials is fire safety. So it's outside of the remit of the structures that we see today. But there are certain composite materials where the matrix material is actually able to be approved in fire certification, which allows that then to be used for battery applications, provided on the structural side, provided that the structure is meeting the integrity requirements, then there's nothing really to stop composites being used at all.
Perfect. So while people are still answering the poll, there's another question that came in. Is OptiAssist available with value-based token licensing? So
unfortunately not.
yeah, for those who are unaware of, within SimCenter 3D, you can buy tokens, which enables you an access to multiple solvers. Fortunately, OptiAssist is not available with the value-based token licensing. So I'm just going to close the poll, put in, show the results. And so clearly, I think majority over here want training and software evaluation.
Okay.
We can, we'll look at the poll results, reach out to you for those who want one-on-one meeting, and those who want a technology benchmark as well as training and software evaluation.
I'm really stunned that people haven't clicked. They just want to buy it. It's always a challenge. I had it once in a webinar where somebody clicked that, and I got really excited. I thought, wow, they're really convinced. And then I found out it was one of my engineering team, so that really spoiled my day.
Perfect.
Excellent.
All right, so there are two more questions that just came in, and I'm just going to get them to you just a second. So the other question is, how long does the optimization take to solve?
That's a good question.
Yeah.
Okay, so the way the process works is when the solution is running, it's in a SimCenter Nastran optimization, and that basically is running multiple iterations of an FEA solve. So if you use your analysis solution as a benchmark, if something takes 5 minutes to perform your simulation in Nastran, you're going to be running between 15 and 30 iterations of that in the optimization. So about 15 to 30 times 5 minutes. If you've got a model that does take a day to solve, that's going to be problematic, but then it takes longer. So it's simply a factor of your simulation time, so to about 15 to 30 times.
Understood. 15 to 30 times in the simulation solve time. Makes sense. There is another question, and this is from David. So do you have suggestions to try integrate topography optimization with startups that don't have the volumes to buy stamping molds?
I have the volume to buy stamping molds. Ooh, that's a good question. Well, if you're working with different manufacturing processes such as molded parts, then you could use some of the linear patterns in the methods, and so you can still see some good improvements in performance. You're limiting the scope of what you can do with your form, but certainly by putting those constraints in there, it can still give you that benefit in terms of performance. I think if I've understood the question, great. I hope I've answered that correctly, David, but please feel free to follow up with me after the webinar if you want to.
Perfect. There's another question. How does OptiAssist differ from HEADS? And for those who are unaware, HEADS is just an optimization platform that uses a genetic algorithm. So
it uses
how is
many.
that different? Oh yeah, true. True.
Okay, yeah, so that's whoever's asked that obviously has got some experience of methods available. So HEADS is what I would describe as a design exploration tool. So it's looking at being able to add the process of optimization to multiple systems. So this can be coupling in CFD with multi-body dynamics, with control systems, with structures all together. You can build an automation and then evaluate the performance of those systems. It's very good at exploring designs. It has typically a much higher hit in terms of engaging and adopting it as a technology, and also the simulation way. If you are running simulations that are quite computation expensive, then there's a big hit in terms of the number of simulations you need. Optisys and its work with Nastran is more targeted on focusing on optimization to give you a design idea, a design solution in sort of the minimum number of iterations, and it's more focused purely on the structural part of things.
Understood.
Okay.
Understood. Perfect. So, Martin, we have time for one last question. We'll take this question
Okay.
and most likely end the session after this. So, the question is for someone who normally created batches of custom one-offs, would you say this would be still be able to cut time and support the specification of the engineered parts as a one-off? So, if people are making custom parts, would it still be able to cut time and support the specification of that one-off part or custom part?
Uh, I would say so, yes. Obviously, it depends on the motivations of what you're trying to get from that one-off part. If it is good performance, I mean, the most extreme example of one-off parts is Formula One. That is quite an extreme example, I realise, but you're really low volume, but you're still maximising performance and making the best efficiency of your part. So absolutely, the technology is there to save you time, no matter how you're manufacturing. And depending on how you're manufacturing those one-offs, it gives you a lot of freedom in terms of what you can achieve with those designs.
Exactly. All right, folks. We've reached the top of the hour. Um, there is one quick question. I guess let's take this as for the last 1 minute. But what is the added value of OptiAssist compared to using the 4 variants of solution 200 that's already available? So Salt 200. What's the value added for OptiAssist?
No problem at all. So again, a good question. There's a slide I've made in the past about this. Is what does Optisys add? And there are two things it really adds. One is it's adding a facilitator for Sol 200, getting the ability to access what clearly you understand is there as an optimization approach inside. So you have sizing optimization, and there are tools for shape and so on in there. But there's no accessibility for how you get to it, and I think the additional methods is the other part that Optisys brings. So it's creating free shape and topography optimization as methods through all the data management and so on. And then in the thickness or the sizing side of things, it's giving much more interactive control of how you can optimize for thickness. So that allows you to bring it closer to design and manufacturing feasibility. Good questions. I like these.
Perfect. I thank you very much, Martin. Okay, so I guess we've already crossed our time. For folks who have further questions, please don't hesitate to contact us. You'll receive an email with a survey form, fill that in, and some of our contact information. And we're looking forward to reaching out to you folks and continuing the conversation. So hope you guys have a great afternoon, great evening, or a great morning, depending on where you're in the world. And we'll keep in touch. So thank you very much, and I hope you guys have a great rest of the
Brilliant.
day.
Thanks for attending all. Take care.
Thank
Bye-bye.
you.